Okay, here we go. Thank you, thank you, thank you. All right.
Are we gonna need a calculator?
I thought you were eating like.
We are live, children. Children, we are live. Okay, parametric equations. So when we do parametric equations, we're not only going to get position, but we're also going to get time. And that's what makes parametric equations different from the rest, is that we get time along with position, okay? So first of all, you start off with a thing called a vector equation. So a vector equation is like x, y, x value, y value is equal to x0, which is your start. This is your starting point. And then t is time, and then a and b is your movement, okay? This is how you move. It's also called your velocity. We'll see that when we do it, okay? And then what happens is that if we want to put it into our calculator, which we will eventually put it on a calculator, we need to have this equation, in a sense, taken apart, so we just have the x parts and the y parts. So if you were to take a look at your calculator and go to parametric instead of polar, and you go to y equals, you get a x of t and a y of t. So your x value at any time and your y value at any time. So we're going to take today equations, start out with vector equations, and we're going to make them into parametric, okay? So example 1, we have xy equals 2, 1 plus a t, 3, negative 1. So first of all, let's write this as a parametric equation. So we're going to go x of t equals, it's not hard, it's very simple. It is going to be a 2 plus a 3t. I just took the x value and then the 3 times the t, and then the y of t, which of t means time, is going to simply be 1 minus 1t. Okay, those are my parametric equations, all right? Now, let's go ahead and graph this. So what's going to happen is we want to graph this and find its position after 1, 2, 3, 4 seconds, all right? Super easy stuff. So we start, here's my start. We're going to start at the point 2, 1. So there's my start. That's t equals 0, okay? That's at time 0. So then our movement is going to be over 3, down 1. So we're going to move. If we're a bug on this paper, we move over 1, 2, 3, and down 1. That's at t equals 1 after 1 second. We'll do the same thing. We're going to go over 3, 1, 2, 3, and down 1. That's at t equals 2, 1, 2, 3, 1, there's t equals 3, 1, 2, 3, 1, there's t equals 4. And what it can do then is draw a vector. Okay? A vector is simply going to be a line that gives us direction. So I'll put the arrow that way, okay? Now, we could put this in the calculator too. So how does it work with the calculator, okay? Well, you've got to go to parametric mode, okay? So that's the first thing I'm going to do is go to parametric mode. And I found that in my calculator. Went to mode, went to parametric, okay? Radians and degrees don't matter. It's only going to matter if you're going to push sine or cosine. That's the only time radian or degree mode matters, is if you push sine or cosine. So it does not matter at all. So who cares? So go to my y of x, and I get x of t, y of t. So I'm going to plug in both equations. I can't put in the vector equation. It won't do that, but it will put it as a parametric. So I'll just go 2 plus 3t and 1 minus 1t. All right? How am I doing? Am I going too fast? You guys with me? Now I have to think about the window. Before I graph this, one of the things about graphing it by hand is I can use the window here, this graph, so that I can see it on my calculator, right? That's why I like to hand graph it. So if I go into my window, I'm going to see a couple of different things. One is t, okay? Now what I have is negative 10 seconds to 100 seconds. That's a lot of time. In fact, we only ran it from 0 to 4, didn't we? Right? So if we just go 0 to 4, we'll see this part of the graph, okay? For time. We just went 0 to 4 seconds, okay? Steps, I went by 1. I went by 0, 1, 2, 3. If we want to increase our accuracy, we can go by 0.1s, which I'll show you, okay? So window, regular window, pretty much here we can go from 0 to, let's see, 2, 4, 6, 8, 10. Well, So let's go from 0 to, oh, maybe 12, okay? Going all the way across. I'm just saying 12 because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, better go 12, 13, 14, 15. Maybe I'll do more than 12. I'll do, how about 20? How's that sound? My y's scales by 1. My y min, it kind of goes down here. -5 might work because you can see I'm down like 1, 2, 3, 4, 5 would work. Max, 5 would work on the y max because the highest we go is 1. Okay, do you see I'm putting my window of my hand-drawn graph into my calculator? So you ready to graph it? See what it looks like, okay? Cool. See, I just went across my page. Do you want me to show it again? Here it goes. You want to see it go? Isn't that cool? Just went right across the page. Now, so if I go to my trace button, here's the best feature of all. Trace. I can get a position and a time. 1 second tells me where it's at. 2 seconds tells me where it's at. 3, 4. And that's all it's going to go, is 4. Now it stops at 4 because I told the calculator to only go from 0 to 4. If I want to see more of it, I go back to my window, right? So, well, I want to see more than 4 seconds, so maybe I want to see how many seconds you want it to run. 12 seconds, right? Now if we do more than 12 seconds, it's going to go further. You guys agree? Yeah. So I probably need to make my Y max more than 20, because it's going to run across the page. So if I take a look here, it's going to go much further after that many seconds. So maybe I'll make my Y max maybe 100. And my Y, maybe -20. I don't know. Anyway, let's graph it. Let's see what happens. Oh, that's not my max. Hold on. I'm going to be messed up. It's going to yell at me. Hold on. 5. There we go. And here we go. There it goes. Nice. And of course, I can do my trace button again. I can find out where it's at any particular time, right? If I want to get more accurate, if I wanted to go and go by 0.1s, I can go back to my window and I can change my steps by 0.1 so I can see it every 1/10 of a second, right? It's every second, I can see it every 1/10 of a second. And it takes longer to graph, but I would have more accuracy, okay? Not too bad. Pretty easy. Okay, let's turn the page. All right. So, example 2. It's just doing the other way. A line contains points 3, 4. There's point A and 1, -2. Here's B, all right? Find a vector equation. So we're going to let A be our start just because it goes from A to B. So A is my start. So if I do my vector equation, let's see. What do vector equations look like? Well, they look like this, don't they? Okay, these are my vector equations. So we're going to write x, y equals my start, which is at 3, 4, plus t times its movement. So you got its movement is from A to B. So we do the x, y. So it has to move back to and down. 1, 2, 3, 4, 5, 6. Down 6, right? So to move from A to B, if we move from here to here, I'm going to go back 2, down 6, right? Okay, then find the parametric equations to describe this. Well, I'm just going to rewrite it as x of t equals 3 minus 2t, and y of t is 4 minus 6t. Pretty easy, isn't it?
Is it going to be this easy on the test?
Well, we're going to eventually do an application. We'll do an application on Tuesday, and you'll see that it gets a little bit more complicated, but the application's a pretty good application, right? What's the velocity? Now, the velocity is our movement. The velocity is the movement. So the velocity is the -2, -6. It's just movement. Movement. All right, there we go. The speed, though, I mean, it doesn't really travel back and down, right? It doesn't really travel back and down. It travels along the line, right? So the speed is going to be the length of this. It's going to be the square root of our -2 squared plus the -6 squared. That's the speed, which is the length of the line, okay? It's going from here to here. that length in 1 second. Okay, that's what the speed means. Okay, so I get the square root of 4 plus 36. I get the square root of 40, which, I don't know, hold on, square root of 40, square root of 40, it's about 6.32, or about 6.32, okay? All right, again, let's graph it on the calculator. We can do that. So you have to do it on the calculator. You have to go to these equations. You have to go to your parametrics, not to your vector. So if I go to my y equals again, let's type in this time a 3 minus a 2t, and we'll type in a 4 minus a 6t. I'm going to check my window. I want my window to work for me, all right? So my window, if I go to my window, I got to make sure it fits my graph. Let's see. 0, 2, we went 12 seconds. I don't need to go 12 seconds. Let's go maybe 5 seconds, all right? Because it's pretty big. And then what I want to do is my x max is definitely here at 3, right? Because it's going to travel that way. My x max is definitely at 3, so maybe I'll make it, I don't know, we can make it 4. And then my x min is going to be some kind of, I am doing this wrong. X max is 4, x min is going to be some negative. We're going to let it run for that many seconds. My x min is probably going to be negative. I'll go negative 10. And if I need to add, I will, okay? My y min is going to be pretty far down, isn't it? Pretty far down in 4 seconds. So I might go, say, negative 30. And my y max is a height of 4, right? So maybe I'll make this 5. Let's graph it. There it goes. All right? And again, if I use my trace button, I can find out where it's at any particular time, okay? Thumbs up?
So is it theoretically going back in time?
No, it's going forward in time. We can. A really good question. We can go back in time. It's a great question. Yes, we can.
Go back to the future.
Yes. So it will allow you to go back in time. So if I go to my window, let's make time, let's go negative 2, okay?
Wait, why haven't they done this then?
Okay, so if we, what's going to happen if we go negative time? What do you think? Just take a guess. Think about this. It's going to take the point further up. It's going to have it start up here. All right, does that make sense? It's going to start up here somewhere. So I better change my max and my min. So my max, I'm going to probably go maybe, I don't know, 15. And my max on my y, I'll probably go maybe 10. If I graph it and go to trace, I can go back in time. There's negative 2 seconds. It's at the point 7, negative 716, negative 1 second, 0, so forth and so on, okay? So yeah, we can go back in time. As far as mathematically, you can go back in time. If it's a story problem, and we're shooting a gun or a cannon or throwing a ball, negative time doesn't make any sense, right? But mathematically, you can say, well, yeah, where was it before it started? That's all, okay? Now, example 2. Okay, a spider travels along the path.
This is example 3, last one.
Yeah, example 3. You know me.
Yeah, done good.
I did.
I wanted to go back in time.
Alright.
What would, yeah, I did. What would be a day if I didn't make a mistake at least once? I just, it's never going to happen, so.
It would be a
Wow, that's
perfect
some good
Friday.
self-esteem.
It'd be a perfect Friday. Negative 2, 5, 1, 2, 3, 4, 5. And I'm going to go 1, negative 2, 1, negative 2, 1, negative 2, 1, negative 2. Okay? So I'm just going to draw this in.
Wait, how'd you graph 1, negative 2?
Okay? So if I did my parametric equations, I'd have x of t for the spider. I'd go x of t equals negative 2 plus a 1t, and a y of t equals a 5 minus a 2t. So the way I graphed it, this is my start. Okay, that's my start, right? And this is my movement. So I'm going to start at negative 2, 5, and then I'm going to move over 1, down 2. Over 1, down 2. So that's my movement, right? So then if I do the same thing with my fly, I'm going to start at 1, 1, right? I'm going to go down 1. Oh, I'm sorry, I did it wrong. I'm going to go over 1, down 1. Nope, 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 nope. Come on, wake up. Start at 1, 1, which is here. Wake up, Mr. Davies. And I'm going to go back 1, up 1, back 1, up 1. There you go. Now,
So it's like we're creating two different types.
right. So if I have the x of t for the fly, it's going to be a 1 minus 1t. And my y of t is going to be my 1 plus 1t. Now, if I look at the two graphs, just looking at the two graphs, it sure looks like they intersect, doesn't it, right? Well, it's kind of like this. If we were to stand at the light at the highway, okay, and if a car drives by, we wait till it drives by, and then we cross, right? If we were just to draw the two paths on a piece of paper, wait. If you were to try and draw the two paths on a piece of paper, it would look like the two lines would intersect, right? And it would look mathematically like there's an intersection, which means the car would hit us and we'd be dead. However, we all know that it's a different time. The car goes by, then we cross, right? So the question is, looking at the graph, it sure looks like the spider eats the fly, right? It looks like it, but I think they're in different times, right? So it looks like this is T1, T2, T3, that's 3, T4, T5. But for the spider, it's T1, T2. Oh, he does catch him, doesn't it? So they are at the same spot at the same time, aren't they? So the spider does get the fly. Yes, he does. He gets them right here because they're at the same spot at the same time. Hold on, let me check. Did I make a mistake?
I think you have to start at 0.
So you start here. 1, 2.
No, the first one is T1. It starts at 1.
Doesn't it start
So
at
the
0?
first one is 1, the second
Did
one
he
is
miss him?
3.
He did miss him. He did miss him. 1, 2, and then 1, 2. He does miss him. He does miss him. No, he does not get him. They miss each other. Let's do that again. 1, 2. Let's put them on the calculator too. Let's check it out, okay? So on the calculator, clear, clear.
Yeah, flies eat spiders.
Spiders eat flies, right?
It says, does the fly catch the spider?
A fly could eat a dead spider, right?
I think flies don't eat.
I don't know, because there is those like little tiny spiders. You could probably eat one of those.
Maybe. Okay, there's the spider. Here's the fly. He's at 1 minus 1t and 1 plus 1t. Change my window so it fits. We'll go from 0 to, say, 4 seconds. We'll go, oh, we don't have to go negative 10. We can go negative probably 5 to 5. We can go like a negative 5 to 5. Should fit the whole thing. And graph them both. So it looks like they do intersect. Let's check the trace button. So here's our first equation, which is the spider. So the spider is at that intersection after 1 second, right?
Yeah.
All right, and then so if I do the other equation,
It doesn't make sense. Shouldn't the spider be
2 seconds, yeah. So he's there after 1 second. And he's there at 2 seconds. They miss each other, don't they? So it's a big fat no. Does not catch him. It's going to be the spider should be ahead.
That doesn't make sense.
So it should, yeah.
So those problems are really bad. This game tear it apart.
Okay. All right, that's what I got.